In this module, we'll be covering the application control features. We will be covering how to create application control lists and how to use them on your traffic. Application control attempts to identify your network traffic by looking at the packets in order to figure out what software is generating them. Application control tries to monitor or prevent the software you want and don't want inside your network. For example, with application control, it is possible to prevent users from using their Gmail accounts. Like anything else, you need to set up the rules for what you want to monitor and what you want to prevent from the list of applications that are available with this feature, which is quite extensive. You can even use application control to rate limit the traffic it detects. This is something that is covered in more detail on the 301 course. You can view the full list of applications and categories from either the FortiGate GUI or the FortiGuard website. But the list that you create dictates what the FortiGate will be looking for. Each entry on the list can be configured differently to block or only log, whatever the situation demands for that software. When you upgrade the firmware or obtain a new device, it will come loaded with a default database that is very small. Be sure to update and run an AV/IPS update, as application control is part of the IPS update. You can add new applications by requesting them on the Fortinet website. Keep in mind, though, that just because you ask for them, it does not guarantee that they will or can even be added. In order to be a candidate in the first place, the traffic has to be unique and identifiable at the packet level from other traffic that occurs on the same port or over the same protocol. The configuration for application control is a two-step process. First, you need to put together the profile that details all the software and actions you want to take with them. Once you have the profile, you need to enable it on the firewall policy you want to monitor for this traffic. Here's an example of the Facebook chat signature. You can see it here in the list, and from there you can click the name to go to the website in order to confirm exactly what the signature is. You can then enable it in the application sensor. It is important to know what a signature actually does and not just make guesses by looking at the name. For example, application control has a signature called login_any. What this signature does is detect the use of software called login_any. As you can see, someone could easily misinterpret this name to mean any kind of login. It is therefore really important to look up the signatures in order to find out exactly what they are meant to detect in the first place before you attempt to use them. You can click the link in each signature to bring up the tooltip. You can also click the link in that tooltip in order to go to our FortiGuard website and read a more detailed description. Packets that are subjected to application control are inspected with these rules from the top down. In this example, Rule 1 says to look for and monitor everything and log it. Rule 2 says to block Skype, but this will never happen because Skype matches the first rule. This is the exact same behavior as with firewall policies. Your filters can be set up on a per application basis or on a group basis. You cannot have an application sensor that contains too many entries, so your best approach is to have generic policies to block the applications you want, like peer-to-peer. If it is not something you are actively investigating, there is no reason to log it, since you would only be wasting your resources. The unit comes with two implicit rules. They are implicit 1 and implicit 2, and by default they are enabled. Implicit 1 is a rule that, if enabled, will inspect your traffic to see if it matches any known application control signatures. Implicit 2 will make logs for anything that does not match a known signature. These show up in the logs as unknown application since the FortiGate unit does not have a signature to match. They are very useful if you are investigating your network to determine what exactly is going on and where your bandwidth is being consumed. You may choose not to log traffic that triggers these sensors in order to free up logging resources until you require this information. Also, just because traffic cannot be identified does not mean it should be blocked. You need to decide which traffic you do and do not want to allow within your network. The first thing to figure out when you create or modify a filter rule is how specific to make it. To set up a generic filter, you simply enable or disable the options you want. The more you know about what is in your network, the more specific you can make the detection. You can also use the Specify Applications option if you know exactly what you are looking for. It allows you to pick from the list. When you set up the rules you want, what you'll see below is a list of the signatures this filter will wind up applying, as well as a total number. If this is too high, make your filter more specific, remove some operating systems, things like that. Finally, at the bottom of the profile, you decide on an action. If any of the listed signatures occur, what should the FortiGate do? Monitor it with a log entry, block it, send a reset packet, or apply traffic shaping. You can view the categories on the unit, but the easiest way to investigate and find out what is available for detection is to use the FortiGuard website. All the software categories are listed along with descriptions to help further clarify what it applies to. Application detection is like virus scanning. Most applications change their traffic patterns over time, so if this is a feature you intend to use, you will need to keep it updated with the automatic updates. Otherwise, it will become less effective over time, just like outdated virus signatures. It is also important to properly identify how a piece of software works. For example, this is the article for Google Talk, which is an instant messenger software with its own signature. Now take notice in the recommended action. It mentions the software actually uses Jabber for communication. So depending on how your application control rules were set up, you could be allowing Google.Talk and still have the software fail and the logs would show Jabber. It's very important to properly research the software you need to keep a careful watch of. This could involve using the internet to find more information and/or making test policies. As well, you should test everything to see if anything will get through or get blocked when you do not want it to. Application control allows you to inspect and apply access restrictions for 4 major IM software packages, including MSN, Yahoo, ICQ, and AOL Instant Messenger. This is handled on the FortiGate device using a single Instant Messenger proxy. Application control is used to identify the traffic, which is then handed over to the proxy for management. Something to keep in mind is that there are no standards for the communications protocols for this software. There are no RFCs or any public standards of any kind. This means that in order to create this proxy, Fortinet developers had to reverse engineer the protocols. It also means that vendors of this software can rework their code for any reason and at any time without telling anyone. This is something to keep in mind if you intend to use application control for IM applications. Normally, when application control is enabled, it is handled by the IPS engine, so it works the same way as flow inspection. There is no proxy, just patterns matching the packets as they pass through. The difference in the case of these IM software products is that in order for the FortiGate device to provide inspection of this, it needs to make use of a man-in-the-middle proxy. With MSN, ICQ, AOL Instant Messenger, and Yahoo, The software is communicating with the FortiGate device, which is pretending to be the server. The FortiGate device then interfaces with the real servers, pretending to be the software. Application control is just a feature used to identify the traffic. This is a look at the options for IM inspection for a specific application. You can choose to block it entirely or just block certain aspects of its use, like file transfers and voice calls. Because the options for these 4 instant messenger applications are so different from everything else, and because they are the only ones that engage a proxy, they are separated from the normal instant messenger group category. While they are instant messengers and technically part of the IM group, in order to enable inspection for them, you must explicitly select them from the application control list. The reason is quite simple. There is no exempt option in application control, so if you were scanning all IM traffic and there was a change in only one of the applications which was causing problems, the only way to bypass inspection would be to manually list all 150 or so instant messenger applications except the one causing the issue. The default policy for IM is to allow all users. Access is restricted based on the application control profile. You can change the policy to deny all users except the ones that you configure. If your policy is to allow, you cannot block based on IM usernames. The GUI can be used to create IM users on the FortiGate device, but only once you have created the first IM user from the CLI. Afterwards, the option appears in the GUI to create additional IM users upon your next login or browser refresh. The username will match whatever is used to log into the service. The protocol will match one of the 4 IM options, and the policy will only be effective if you change the IM policy to deny in the CLI. Otherwise, the unit will only look at the username for the purposes of log entries. With an IM policy of allow, this block user policy will never get processed by the device. Again, the user list will only be checked if the policy is set to deny. Once you create an IM user, an additional option will show up in the GUI which allows you to monitor the IM proxy. It displays a list of users that are logged in and the instant messenger application they are currently logged into. You can adjust the filters to display only the users that are logged into a single application by changing the protocol. You can also adjust the users list to display only online users or blocked users. You can also use application control to perform traffic shaping for the purposes of limiting a particular kind of traffic. This is very useful when you are trying to limit traffic that cannot be separated using port numbers in a firewall policy. Some high traffic websites like YouTube or Facebook can be traffic shaped in this way. Let's say that you enabled application control because you wanted to investigate a bandwidth issue inside your network. Users had been complaining of slowness, and during peak times, resources were maxing out. During the investigation, you found that many of the users were using Netflix, especially during these high traffic times. You could rate limit them. Because Netflix is just web traffic, you could not separate this traffic using a firewall policy by port or destination IP, since the destination is distributed. You could create a shared traffic shaper to apply to Netflix and then use application control in order to limit the total amount of traffic that is allowed to use. This would keep it from saturating your network. You can do the same with YouTube videos or any other application control entry utilizing the bulk of your network resources. Before applying this, however, you should carefully consider what you are applying it to. For instance, if the situation was different and you found that FTP traffic was the main cause of the bandwidth issues, there would be no sense in using application control to identify that. A policy for port 21 traffic can identify FTP traffic using fewer resources than using application control. It is a very simple reality that most people do not actually understand how the software they are using actually works. To illustrate this, let's try a little experiment. How does this feature actually work? Essentially, it scans traffic passing through the FortiGate looking for patterns. It's really just as simple as that. A particular application entry, like Google Talk, is just a series of transmission patterns in the packets that identify the application. What that pattern actually is obviously needs to be unique for the application. Otherwise, you can only use a generic signature. Not every application behaves in a special fashion. Many of them simply use pre-existing standard protocols and communications methods. This is not an active scan of either system. Doing this would require software to be installed on either end. It's a passive scan of the traffic patterns and nothing else. One of the most often used aspects of application control is the ability to detect, monitor, and prevent peer-to-peer software. This keeps all of those torrents from chewing up your network bandwidth. For those who are not aware of how peer-to-peer file sharing actually works, here's a brief explanation. Standard file transfers happen between a single client, single server with a defined protocol over a set port. Be it a website or an FTP site, it is easy to detect and limit by the fact that there's only one sender and one receiver. Easy to detect and easy to limit. Also, because you only have a single server, in order to get high transfer speeds, you need to invest a large amount into the server hardware. This also helps keep speeds reasonable. Peer-to-peer transfers a single file using multiple, theoretically unlimited senders. So imagine if you had 15 different devices all sending you different parts of the same file. Neither one of these devices needs to be very powerful, but the effective speed you will get quickly outperforms the alternative. Also, since there are no maximum number of devices that can send you files, this can quickly consume huge amounts of network bandwidth. But this still does not answer the big question. Why is peer-to-peer traffic so difficult to detect? When HTTP and other protocols were designed, they were built to work. Designers did not care if they were easily detectable. What they wanted was for it to be distinct from other protocols. When the peer-to-peer protocols were designed, the designers wanted them to be incredibly hard to detect. So things like port randomization and sudden changes in the traffic and encryption patterns were built into the behavior as standard. They are hard to detect on purpose because they have been built to be hard to detect. The protocol shifts and changes actively in order to avoid detection. Now it's time for the labs. This time we'll be working with application control. Exercise 1 will have you set up and try out an application control list. In this class, we will show you how to route packets through your FortiGate using static routes and policy routes. Dynamic routing protocols such as BGP are only mentioned briefly. They are not the main focus of this course. Here's an overview of what we will talk about. We'll cover not only routing concepts and configuration, but also troubleshooting. When we say routing, of course, specifically we mean how to route based upon packets IP layer. Some protocols can be routed or dropped based upon network addresses or other parts at a higher layer of the network protocol stack. Voice over IP and HTTP are the most common. For example, HTTP proxies often drop or redirect requests based upon the URL in the HTTP header. Those higher layer protocols are not the focus of this class though. We will be focusing mainly on IP sessions. After completing this class, you should have these practical skills that you can use in basic or complex FortiGate routing. Lab exercises can help you to test and reinforce your skills. What is routing? Routing decides where FortiGate will send packets that it receives and that it generates. For example, FortiGate can check the destination field of the packet's IP header. If routing rules match that destination, FortiGate can transmit the packet from port 1 instead of port 2 towards router 1 instead of router 2. If an allowed packet is not destined for the FortiGate itself, not administrative access for example, FortiGate must relay the packet. FortiGate searches for matching routes that it can use to deliver the packet. FortiGate either delivers the packet directly to its final destination or relays it to the next router along the path towards the destination. Usually, FortiGate sends a packet from a receiving network interface, known as ingress, to the exit, egress, indicated by the route, for example, from LAN 1 to WAN 1. Packets from the LAN 1 should exit from WAN 1 only if the destination is somewhere on the Internet. However, as we'll see later, you can decide to route packets using more than just the destination IP addresses. Sometimes, a network interface is virtual and it doesn't correlate to a physical port. Also, if the routing directions are misconfigured, packets will not reach their destination. Packets will be lost. How does FortiGate decide routes? FortiGate has multiple routing modules. This diagram shows the logic between them. First, FortiGate searches its route cache. You can view that with the CLI command diag IP RT cache list. If it finds a match, it will transmit the packet to that subnet. If there was no match, next FortiGate will search its policy routes. You can view them with the command show router policy. Finally, FortiGate searches the forwarding information base, also known as the FIB. The FIB is generated by the routing process and is the actual table for packet forwarding once IP sessions are established. How is the FIB related to the routing table? Think of the routing table's purpose as for management, while the FIB is for forwarding. This separation becomes more clear in FortiGate Active-Active HA. In an HA cluster, both route management and forwarding exist on the primary FortiGate, but on the secondary FortiGate, only route forwarding exists. It merely follows route management queues from the primary. If there is no match in any of those tables, the packet will be dropped because it is unroutable. Where can you find most routes that FortiGate is currently using? For the routing table in the GUI, go to Router, Monitor, Routing Monitor. There is no Configure button. This is a type of compiled cache that is loaded into memory. In simple cases, it basically is the same as the FIB used by the kernel. Routes can be added manually or automatically. Policy routes may exist separately, so it usually doesn't exactly match your list of manually configured routes, although they are related. We'll discuss exactly how they're related next. What isn't loaded into the routing table and what is extra? FortiGate may omit some routes from the cache. Only the paths with the fewest routers between FortiGate and the destination, for example, are worth adding. A smaller table makes lookups faster. FortiGate wants to load and use only the best routes. We'll look at which manually configured routes are loaded next. FortiGate also loads policy routes into a separate table, so those lookups occur in a separate table. Automatically created routes can appear. FortiGate will automatically create an entry when you directly connect any device with an IP address. On larger networks, your FortiGate may also receive routes via protocol such as BGP from other routers. Routers can use dynamic routing protocols to automatically announce and organize routes. Remember, if you compare the routing table to your total manual routing configuration, expect differences. This is the logic of routes that are loaded into the routing table. Routes are only loaded if the interface is currently both physically linked and administratively up. If the cable isn't plugged in or if a Wi-Fi network has no signal, for example, packets can't be transmitted along that path. All routes through that link will be temporarily unloaded from the table until the link is available again. We will talk about dead gateway detection later. When two or more routes have the same destination subnet, only the ones with the smallest distance are included. If the distances are equal, only the routes with the smallest metric are included. If the metric also is identical, then depending on the dynamic routing protocol's rules, FortiGate will select which one to include in the cache. In the routing table, each of those entries has a few pieces of data such as distance. They are used to relay or deliver each matching packet. Destination IP addresses and gateway routers are self-explanatory. But what about the distance, metric, and priority? How do they affect which routing path packets will use? Let's explain each briefly. Distance is the second factor that the FortiGate will consider when deciding which route to include in the routing table. FortiGate wants to route packets along the shortest path. As you can see though, distance is not measured in meters or inches, but by the number of times that more routers must relay the packets to reach the destination. Processing can take more time than transmission between points. Electrons moving through copper or radiation through space are relatively fast. Unless by chance the default distance is accurate for your specific network, you should configure the setting. Note that you can't configure distance for directly connected devices, such as an email server whose cable is plugged in directly to port 4. But you don't need to. Directly connected devices inherently have a distance of 0 since there is no router between the FortiGate and the destination. Metric, as you can see, is similar to distance. If your network is simple, often you won't notice any effect when you change this setting. After distance and metric, FortiGate will compare routes' priorities. FortiGate will use the route with the smallest number configured in the route's priority setting. In other words, if we have two routes with different priorities to the same destination, only the first route with the smallest priority will be used. Note that unlike with distance metrics, both are loaded into the routing table. However, only the route with the smallest priority number is used. Now that we've looked at what the routing table is and how FortiGate uses it, let's configure routes. One type of manually configured route is called a static route. In the route table, its type column is static. We are manually telling the FortiGate device when you see a packet whose destination is within this specific range of destination addresses, send it through this network interface towards this router. We also configure the distance and priority so that FortiGate knows which routes to load into memory and in what order. For example, in simple home networks, DHCP automatically retrieves and configures one static route. Your modem then sends all outgoing traffic through your ISP's internet router, which can relay packets to their destination. When do you not require a static route? When a destination is cabled directly to one of the FortiGate's network interfaces with no router in between. FortiGate will be aware of the direct link. In the routing table, its type is connected. Static routes are simple. Policy routing, however, can consider more factors when deciding the route, such as the source address, port numbers, and other parts of the IP header. As the name implies, policy routes have precedence over the routing table. So if a packet matches a policy route, it will bypass routing table lookups. Remember what FortiGate considers a match. The route must be valid in the normal sense. A destination and gateway are required, and no disconnected or downlinks can be used. For policy routes, though, packets also must match all subnets, TOS bits, and port numbers that you specify. So if a setting shouldn't be a criteria for matching, leave it blank. Manually configuring distances and priorities in large networks can be time-consuming. how can we configure routes more quickly? For large networks, manually configuring hundreds of static routes and policy routes may not be practical. Your FortiGate can help by configuring routes automatically. FortiOS 5.0 supports several dynamic routing protocols: RIP, OSPF, BGP, and ISIS. In dynamic routing, FortiGate communicates with nearby routers to discover their paths and to advertise its own directly connected devices. Discovered paths are automatically added to FortiGate's routing table, so verify that your neighbor routers are trusted and secured. Larger networks also may need to balance routing load among multiple valid paths and detect and avoid routers that are down. We'll discuss that soon also. Dynamic routing protocols require access to an interface that is always up. A loopback interface isn't correlated to any of the FortiGate's physical links. It exists in the FortiGate software only. So all traffic with that destination stops at your FortiGate, and it is always up and available regardless of physical cabling. To create a loopback interface, you go to System, Network, Interface, and click on Create New. The type must be Loopback Interface. In larger networks, in addition to dynamic routing, there is also often more than one way to reach important destinations. When two or more routes to the same destination exists, and they have an equal distance, FortiGate can use equal cost multipath, also known as ECMP routing. This will load balance traffic amongst gateways. Most networks presume stability and predictability. Therefore, the method most often used is the default one, which uses a hash of the source IP to guarantee the same route for every packet from that source. With the other two methods, the gateway used will change from one packet to the next, so you cannot predict where your traffic will go. If an interface becomes unavailable either due to physical disconnection or due to dead peer detection, all routes associated with that link gateway are temporarily removed from the routing table cache. So, if WAN 1 went down, its routes would be dropped from the routing table. The only remaining available route for traffic would be through WAN 2. When WAN 1 comes up again, then its routes will be loaded into the routing table again. If you do not want to load balance, you can change which routes will be primarily used for the traffic. You can change the priority number. Both routes have the same distance, and so they are both already in the routing table. FortiGate doesn't need to load or unload any routes. By changing the priority, FortiGate will simply switch to use the route with the smallest priority number. To edit a route's priority, open the Advanced section. Dead gateway detection is a mechanism for detecting when a router along the path is down. Often it is used where there are redundant routers on site, such as an HA deployment or for dual ISP links. When configured, FortiGate periodically sends signals through one of the gateways to a server that acts as a beacon. The server can be any host that should normally be reachable via that path. Usually, it's best to choose a stable server with robust infrastructure and to choose the protocol that the server would normally respond to. Notice that this doesn't test all vectors from the gateway to other destinations, so also consider that if some routers downstream don't have a redundant deployment, they could break the path between the FortiGate and many destinations. It may be useful to choose a server that is indirectly attached, located 1 or 2 hops beyond the route's gateway. This does not exactly test availability of this one gateway, but rather the combination of gateways. That way, dead gateway detection will accurately indicate availability of services and subsequent hops. If most destination and services are not available, then the route might be effectively dead even if its gateway is up. While a server is unresponsive, FortiGate will continue to send dead gateway packets. As soon as FortiGate receives a reply, it will reinstate that gateway's routes. Here is where you configure the dead gateway detection. You must enter the egress interface, the IP address of the gateway router, and the IP address and the protocol, ICMP, UDP, or TCP, of a beacon called a ping server that is beyond that gateway. If your network uses dynamic routing protocols, dead gateway detection and direct connections are not the only way to avoid routers that are down. Bidirectional forwarding detection, known as BFD, is a mechanism for detecting when a neighbor router fails. It is used for faster route convergence of the BGP and OSPF routing protocols. Once a connection with the neighbor router is established, both FortiGate devices monitor each other to see if their neighbor remains available. If the other FortiGate does not respond, the responsive FortiGate will change routes accordingly to avoid its unresponsive neighbor. BFD can only be enabled from the CLI and only for OSPF and BGP. Most routes are used to build a path so that the source can reach the destination. Blackhole routes do the opposite, making the destination unreachable. Sometimes administrators require the use of wide summarized subnets to avoid unnecessary traffic. Traffic to unused subnets must be dropped. To do this, you can create a blackhole route to silently drop unwanted traffic. Blackhole routes should be used with caution. Improperly used, they will disrupt traffic. In the above example, all spoke sites, router 3, router 4, etc., use addresses in the 172.16.0.0/16 range. They have a routing protocol within their domain to reach the specific 172.16.x.0/24 subnets. They also have a default route to access the Internet. The link between router 1 and router 2 is static only. A packet sent from router 3 whose destination is in the 172.16.0.0/16 range but to a /24 network that does not exist will take the default route path. Router 2 will then forward to router 1 and router 1 will bounce this back to router 2 because of the summarized static routes. This will continue until the packet TTL drops to 0. To prevent it, router 2 should have a blackhole route for the network 172.16.0.0/16. If a packet is destined to a subnet 172.16.x.0/24 that does not exist, it will be dropped and not forwarded to the default route path of router 1. Packets are sometimes dropped for reasons where routing and security are related. Reverse path forwarding, known as RPF, is a mechanism that protects the FortiGate and the network from IP spoofing attacks. It checks if there is a valid route back to the packet's source through the interface where the packet is coming from. If there is not a valid route, the packet is dropped. When packets are dropped because of the RPF mechanism, the debug flow outputs an error like the one shown in this slide. We'll talk about how to enable the Diag debug flow shortly. Here's a sample network setup and routing table. There are two routing errors, two interfaces that won't route traffic properly. Can you see what they are? Port 1 and WAN 2. Port 1 will not route traffic properly. The reason is because of the subnet for the computers. They're in the 10.0.0.0/24, and there's no route for that subnet in the routing table through that interface, port 1. So anything coming from 10.0.0.0/24 to that interface will be dropped because that subnet cannot be routed back. This is fixed by adding a route to 10.0.0.0/24. Now when the FortiGate does the RPF check for the incoming packet, it finds a valid route to that subnet throughout port 1. The packet is now accepted. The other interface that will not be able to route traffic properly either is WAN 2. While it is physically connected to the Internet, The only IPs that would be valid as sources or destinations would be those in the 2.2.2.0/30 subnet, so incoming internet traffic will not pass the RPF check and will be dropped. Once again, this is fixed by adding a route for WAN 2. In this case, the route needs to act as a default gateway in order to provide internet access. To become part of the routing table, it needs to have the same distance as the default route for WAN 1. They both can have different priorities, but as we saw in previous slides, they must have the same distance to be included in the routing table. If the priorities are the same, this creates a situation like ones we saw for ECMP. So if the destination is the internet, there are two possible paths to take through WAN 1 or WAN 2. Some sessions will exit from WAN 1 and others will exit from WAN 2. Reverse path forwarding can either be strictly or loosely enforced. Loose RPF checks that the sender can be routed out from the interface where the packet was received. This simply confirms that a response is possible. Strict RPF requires that the receiving interface is not only valid, but it is also the best interface for the reply. If you have multiple routes, it must be the preferred one. The behavior of this feature is defined by the RFC 3704 published by Cisco. Let's look at an example of loose RPF. In this case, 20.20.20.20 pings 10.10.10.5 but fakes a source IP of 10.10.10.6, making the packet appear to be initiated from the internal network. Loose RPF would allow this because the route on WAN 1 is a default route of 0.0.0.0, which is valid although not the best. What would happen next is that 10.10.10.6 would send the SYNAC packet to the real device with the IP address of 10.10.10.5. But since 10.10.10.5 is not expecting a SYNAC packet because it had not previously sent any SYN packet to .6, it will reply with a TCP reset packet. Let's see what happens in the same topology with strict reverse path forwarding. Strict RPF drops the packet. The default route in WAN 1 is a valid route to the subnet 10.10.10.0/24, but it is not the best route. The best route is through the internal interface, so the packet should have been coming from the internal interface. Although strict RPF is more secure, it can backfire if you use dynamic routing. Dynamic routing can change quickly, and this fact combined with strict reverse path forwarding could cause FortiGate to drop packets each time the preferred route changes. Multicast is traffic sent from one source to multiple destinations. A multicast routing protocol populates the routing tables with information about how to route multicast traffic. Multicast is commonly used for video conferencing because it lowers the origin's resource usage and hardware requirements of transmitting to multiple destinations. One stream of data goes to the router, which then multiplies that into data streams for each destination. Link aggregation is when multiple physical interfaces are logically bound into a single channel. This increases bandwidth and provides redundancy. A FortiGate operating in transparent mode can be inserted in the middle of an aggregated link to inspect the traffic. We've seen the routing table in the GUI. Now let's see some diagnostics that you can use in the CLI. This is the equivalent CLI command which shows the routing table. At the top, each code is defined. Each route begins with a flag that shows what kind of route it is and how it was learned. After the flag, there is the route itself, then the distance and metric. Next you have the gateway, if there is one, and the egress network interface. Finally, for dynamic routes, you have a timer that indicates when the route will expire if it is not renewed. The previous command only shows routes that are currently loaded in the routing table. To show routes that are inactive, you can use this command. For example, this route is inactive because it has a distance of 10, and there is another route to the same destination that has a smaller distance of 5. Only the shortest available path is loaded into the routing table. This command is rarely used and is very low level, but it shows the actual forwarding information base, which is indeed the routing information that the kernel uses to forward traffic. This command gives a quick list of IP addresses associated with each NIC. They can be physical, VLAN, or virtual interfaces. Depending on the situation, you may need to look at the ARP table. This command is used for that purpose. It shows the interface, IP address, and associated MAC address. If you use dynamic routing protocols, you can get more information by using this command. It gives detailed information about how the FortiGate is configured for the various dynamic protocols. This is the command we can use to check the status of all the dead gateway detection entries. It shows, for each interface, which detectors are active and their status up or down. For example, in this case, the gateway 10.200.4.10 for the interface port 2 is down, which means that all the routes using that gateway will be dropped from the routing table until the gateway is available again. FortiGate has a built-in packet capturer, also called a sniffer, that can be used to record traffic for troubleshooting. To use it in the GUI, go to System, Network, Packet Capture. In a few slides, we will see some examples of how to filter which packet it records. Running the sniffer from the GUI requires a formatted hard drive. Not all models of FortiGate have one. Once the sniffer has finished, you can download it in standard PCAP file format, which can be opened with a protocol analyzer such as Wireshark. Alternatively, you can use the CLI to run the packet sniffer. In this case, a hard disk is not required, so it can be used on any FortiGate model. When using the command, you must specify which interface, or any to display packets from all the interfaces, a filter, a verbosity level, and optionally the maximum number of packets to capture. The verbosity level is a number from 1 to 6. This slide shows what information is displayed in each level. 4 is the most commonly used level. The syntax in the filter follows the TCP dump standard. You can filter the output to be very specific. This is important during high traffic volumes. If the filter is not specific enough, the output may overwhelm the sniffer's ability to display all matching packets. Also, when running the sniffer from the CLI, the output is displayed in real time on the console, not downloaded as a PCAP file. Therefore, you must either read the output on the fly or configure your terminal emulator to save output to a text file. Packet capture is done by the kernel. To reach the kernel, traffic must pass through circuits leading to the CPU. However, offloaded traffic, by definition, is mostly processed by the NP accelerator chips. Only the IP session initiator is handled by the kernel. If you need to capture all of the session, you must temporarily disable hardware acceleration first. This can be done on a per firewall policy basis. Remember, this change will impact performance. The traffic matching the firewall policy where you have disabled NP acceleration will be processed more slowly. Hardware acceleration should be immediately re-enabled after finishing the sniffer. One of the best ways of tracking down session creation and policy matching is to use diag debug flow commands. When enabled, FortiGate will show step by step what the kernel is doing with each packet. To show the packet processing flow messages,
we must first type these 3 commands to enable the logging output. Then we specify a filter. We can filter by source or destination IP address or port. However, usually the best option is to use the option ADDR to filter by an IP address regardless of the direction of the traffic. The address can be either the source or destination. The ADDR option will match both. Finally, the number of packets to capture with the command diag debug flow trace start. Usually, 10 packets are enough to troubleshoot most issues. After packet flow output is finished, remember to stop it with the command diag debug flow trace stop. This slide shows a commented output of a typical diag debug flow command for HTTP traffic with NAT. It shows what the kernel does with each packet. Output shows packet arrival, session creation, route matching, firewall policy matching, packet egress. In this example, the filter shows both traffic directions. So on the right side, we see the logs related with the reply. For NAT, the output shows when NAT is applied to source or destination IP address. Now it's time for the labs. In this lab, you'll look at the behavior of static routes on a FortiGate. Exercise 1 is basic connectivity testing. You'll probably use this skill in the other labs. Exercise 2 will be about dead gateway detection. Exercise 3 will cover failover and load balancing situations, or ECMP from the presentation slides. Exercise 4 will test your static routing failover configuration.